Hey y'all, welcome back. I'm Mr. Boyden, your personal math teacher, and today we're going to be continuing our learning on sampling distributions by talking about what happens with a sample mean. In the previous video, we talked about sample proportions and how they work, and you're going to see a lot of similarities in this video and in this concept. Conceptually, they're very similar. There's a couple of key differences that I'll call out as we go, but in terms of is it a new concept? Not really. So let's get right into it. Okay. First thing is the mean is basically the same way it worked. The mean of the sampling distribution works the exact same way it did with proportions, where the mean of the sampling distribution of x bar, and it's x bar now because we're talking about means, not proportions, it's the same as the mean of the entire distribution. So quick reminder that mu right here is referring to the population, whereas x bar is referring to the mean of any one sample. Both means, but of different things. Okay. Now, what about the standard deviation? This is a difference. Okay, so for your notes, you're going to want to make sure you have this. The difference, and I'll highlight it, is right here. It's a different formula. Now, if you think about it, that makes sense. We couldn't use the proportion formula because, or the standard deviation of a proportion formula because it required knowing a proportion. And today we're talking about means, not proportions. So you'll want to make sure that you know that the standard deviation is calculated slightly differently. Now, we do still have to meet the 10% condition on this. And so I want to remind you what that is. That's identical as it was in the proportions video. So that's that the sample size needs to be less than 10% of the population size. Okay, and that's how we would show that as an equation. Now, number 3 is another key difference, and so I'm going to highlight that in green so that stands out as something that's new. But there's a similarity too. Just like with proportions, we used the large counts condition to justify why the sampling distribution was approximately normal. This is still a justification of approximate normality, except when we're talking about means, we have to use the central limit theorem. Now, what the central limit theorem requires is that our sample size is 30 or larger. And so long as we have this, we get to claim that the sampling distribution is approximately normal. Before you allow the video to go any further, please pause and write down anything that you want to, and then we're going to get right into some examples. Let's look at our first example. As always, I want you to be invited. I want to invite you to pause the video and try these examples on your own. There's a chance that maybe you could do it right now, and if you can, you'll get way more out of doing it yourself than out of just simply watching me do it. So here we go. The length of human pregnancies from conception to birth varies according to a distribution that is approximately normal, with a mean of 266 days and a standard deviation of 16 days. We need to find the probability that a randomly chosen pregnant woman has a pregnancy that lasts for more than 270 days. Now, there's something interesting in this question. Did you notice that A is underlined? A randomly chosen pregnant woman? The reason they're calling that out is it's not a trick question, but it's one of those questions that's so easy that you might get it wrong because it's so easy. Okay, so up here, what we just learned is how to calculate the standard deviation of the sampling distribution of x bar. But this only happens when you're sampling with a sample size that's more than 1. And that's why you have that condition down here for the 10% condition. But this is just choosing one woman. Okay, and so we already know the standard deviation of that. That's 16 days. So this is just a normal distribution with the mean already known at 266, and they've asked us what is the probability that a randomly chosen pregnant woman has a pregnancy for more than 270 days. Let's put 270 on here. And this is our shaded region. From here, we can go right to the calculator and just type it in. Okay, so give me just a moment. I'll pull up my calculator here. So I'm going to go to my statistics menu, and it's in distributions, and this is a normal CDF. And we know it's normal because they told us so. So up here, we'll type in 270 for the lower bound, sorry. Our upper bound is infinite because they just said greater than. They told us the mean of 266, and they told us the standard deviation of 16. So 0.401 are the digits that I'll keep. Okay, and that's all that one is. That actually is a throwback to like Unit 2 or 3 in the beginning of the course. Let's keep going and see if it gets more interesting. What happens in the next part? So now they say we are going to be choosing a simple random sample of 6 pregnant women. Now we're starting to get into the sampling distribution because you have a sample size that's more than 1. Okay, so we allow x bar to be the mean pregnancy length for the sample, and now we get to find the mean of the sampling distribution. And we also get to calculate and interpret the standard deviation of the sampling distribution for x bar, verifying the 10% condition is met. So what I want to do is I'm going to scroll up for a second and review what we saw in the very beginning of the video. Okay, the mean of the sampling distribution of x bar is just mu. And in this question, they told us that. They told us it was 266. What about the standard deviation of the sampling distribution? Well, now we get to use this formula. Okay, sigma sub x bar is equal to sigma over the square root of n. So here we go. The mean of the sampling distribution, it's exactly what they told us above. The mean of x bar is 266. The standard deviation is sigma over the square root of n. And they gave us both those values. Okay, we're sampling with sample size of 6, and they told us up above that the standard deviation of the population is 16. So 16 over the square root of 6, and let's just go ahead and type that right in the calculator. So 16 divided by square root of 6 is 6.532. Okay, we're asked to interpret that and verify that the 10% condition is met. Now, when we're interpreting, this is the old-timey response, that golden answer that uses the word typically. Okay, so what this is saying is when taking a sample of size 6, taking a sample with n equals 6, our sample mean, which is x bar, will typically vary from the true mean, which is mu by 6.532. There's our interpretation. What about the 10% condition? Okay, our sample size was 6, and so we need 6, so 10% condition. 6 needs to be less than 10% of, did they tell us what the population is? The population is, it's all pregnant women. So do we think that 6 is less than 10% of all pregnant women? Or really, it's all pregnancies, really. Pregnancies. Yeah, I think it's pretty clear that 6 is less than the number of all pregnancies. In fact, I'm hoping this video gets enough views to verify that, because every one of us who watches this was born, and I'm hoping that more than 60 people will watch this video at some point. And so, yeah, that's a for sure, for sure. Guys, for a test or for the AP exam, you can just say that 6 is less than 10% of all human pregnancies, and you can leave it at that. Okay, you actually don't have to know how many human pregnancies have ever existed. All right, now we get to do a calculation. Find the probability that the mean pregnancy length for women in the sample exceeds 270 days. Okay, now let's compare that to question 1. In question 1, they said find the probability that a randomly chosen pregnant woman, and down here they say find the probability that the mean of a sample. Okay, so this is where we use the mean of the sampling distribution and the standard deviation of the sampling distribution. And yet, the bounds are the same. So let's draw this out. Okay, we know that it's approximately normal. Why? Because up here they said that the actual distribution is approximately normal, and anytime the actual distribution is approximately normal, the sampling distribution will always also be approximately normal. So let's draw this out. So 266 in the center, 270. Now the picture looks the same so far, so you might think, well, it's the same answer. Not so fast. The standard deviation, though, on this one is 6.532, because this is the sampling distribution. For a sample of size 6. Okay, now everything else is going to be the same. And so we're going to jump right back into the calculator. And actually what I'm going to do is I'm just going to modify this calculation from last time. Because the bounds are the same, the mean is the same, the only thing that changes is the standard deviation. And we now know that that number is 6.532. And let's see how that changes our probability. Now we're down to 0.270. Okay, and if you think about it, that should make sense. We know that the actual mean, or let's say, assuming the actual mean is 266, it's less likely that a sample of 6 women would return a value further away as opposed to a single woman. Any single woman being 4 days, I guess you would call having a 4 days longer pregnancy, being 4 days later than your due date is not super surprising. But if you started having a bunch of women that on average were later than that, then that would make us start to question if 266 was the real mean. And that's why it makes sense that this probability is lower than the initial probability for just a single woman of 0.401. Let's try another question. Here's another one. Again, I want to invite you to pause the video, try it on your own. Let's see how you do. Let's try it. Keith is the manager of an auto care center. Based on service records of 3,500 customers from the past year, the time in hours that a technician requires to complete a standard oil change and inspection follows a right-skewed distribution with mu equals 30 and sigma equals 20. For a promotion, he randomly selects 40 current customers and offers them a free oil change and inspection if they redeem the offer during the next month. Keith budgets an average of 35 minutes per customer for a technician to complete the work. Will this be enough? And then we have some questions that follow below. Question A, describe the shape of the sampling distribution of X bar for samples of 40 randomly selected customers. Justify your answer. All right, so we'll talk about the sampling distribution in a second, but let's talk about the overall distribution. They told us that the distribution was right skewed. And so now we've taken a sample of size 40, and they're asking us, what is the shape of the sampling distribution? Well, remember earlier in the video when we talked about the central limit theorem? The central limit theorem tells us that so long as our sample size is 30 or larger, the shape of the sampling distribution will be approximately normal. So the answer to this is approximately normal. And why? We need to justify it. The central limit theorem. Okay, and what we would show here, we show that 40 is greater than or equal to 30, and that's the reason why, due to the central limit theorem, the shape of the sampling distribution is approximately normal. There's nothing more to say than that. Pretty cool, huh? Let's go to part B. Find the mean and standard deviation of the sampling distribution of X bar and be sure to check the 10% condition. Okay, well the mean is the same as the mean of the original distribution. And so what did they tell us that was? They said that was 30, and so that's still going to be true. So mean is still 30. The standard deviation of the sampling distribution is related to the original parameter of the standard deviation because it's sigma over square root of n, and they told us that the standard deviation was 20 divided by the square root of, where's our sample size? They say that Keith randomly selects 40 current customers, so square root of 40. And we're going to put this in a calculator. My experience is that this number is typically a decimal. It's not like a regular math class where it just works out with a nice fraction or something like that. So square root of 40. And in fact, in a contextual question like this, it's not, in a lot of ways, it's better to have a decimal because it's easier to interpret it and understand it. And so typing that in, I get 3.16. 10% condition. So we need to check that our sample size is less than 10% of the population size. And so what does that look like? I'm going to label this as the 10% condition. That would look like a sample size of 40 should be less than 10% of, there are 3,500 service records, so 10% of 3,500. You're welcome to use a calculator here if you'd like to. This simplifies to say that 40 is less than 350. That's true. And so we've now checked the 10% condition as well, which remember, in order to use this formula up here, the 10% condition has to be satisfied. So I actually technically did it out of order in this example, and I think I did it out of order in the example above as well, but it ended up working in both cases. Okay, let's go on to C. We need to calculate the probability that the average time it takes to complete the work exceeds 35 minutes. Well, let's use the information that we have above. We already said that it's approximately normal in part A, and in B, we found the mean and the standard deviation. So I always draw a picture of the normal distribution. For whatever reason, it just gives me a high degree of confidence in knowing what to do in the calculator. So 30, they asked us calculate the probability that the average time it takes to complete the work exceeds 35 minutes. So 35 is there. Exceeding 35 minutes. And so now we can head on over to the calculator and type this in. Now in the calculator, of course, you're welcome to go through the menu. I find that it's a lot quicker if I just modify the command from before. And so I'm going to go back in here. So the mean, or these are the bounds. So the bounds from, I forgot, I better refresh real quick. 35 and above. So 35, the upper bound is still infinite. The mean is 30, and the standard deviation is 3.16. And let's see what this probability is. 0.0568. So what would that be? That's like 5.7% of the time. So if you had a sample of size 40, it could happen sometimes, but it's not going to be happening that often that the mean of your sample would exceed 35 minutes. All right, and this will be our last question. How much average time per customer should Keith budget if he wants to be 99% certain that he doesn't go over budget? For this question, let's remember what we know. We know that the sampling distribution is approximately normal with a mean at 30. And remember that 30, that's a number of minutes. Now in the question above, they initially talked about Keith, and it starts right here. Keith budgets an average of 35 minutes per customer. And so the reason I bring that up is when they say down here, how much average time should Keith budget, it's saying basically how much time does he need to allow for each person, and if it takes longer than that amount of time, then he's gone, quote unquote, over budget. So there's some amount of time over here, X minutes, that's the answer to this question. He wants to be 99% certain that he will not be over budget. That means 99% under budget and 1% over budget. So I can draw this in. That makes this region 0.01 and this region 0.99. And remember that we're going to bring with us these statistics from up above, that the mean is 30 and the standard deviation is 3.16. So what are we going to do in the calculator for this? It's a little different than all the other calculations we've done today. Everything else we've done today, we've known the bounds and we've been looking for a probability. This is the reverse of that, or you might even say the inverse of that, because now we know the opposite information. We now know the area or probability, and we're wanting to know a bound or an x value. So this looks like it's probably an inverse normal calculation. Okay, let's go try it in our calculator. So, statistics, distributions, inverse normal. We'll type in the area. Now remember, you're always typing in the area on the left side. That's how the calculator interprets this. So then 30 is the mean, and the standard deviation was 3.16. Let's see what we get. 37.35. 37.35 minutes. Okay, so if he budgets, or if he allows for, on average, 37.35 minutes, what is that, 37 minutes and 20 seconds, 21 seconds maybe? If he allows that much time per customer on average, then on average he's not going to go over budget, and he will have typically enough time to help his people. So people, that's our introduction to sample means. Hopefully you enjoyed it, and I will see you next time.